Let's take a look at number 3 here in section 10.4. We're to consider this series and determine whether it is convergent, converges absolutely, conditionally, or not at all. So we will again, because to see if it's convergent, absolutely convergent, we're going to take the absolute value, which basically this sign changer up here, -1 to the n, just becomes +1. And let's take a look at this series. Now the terms that we're adding up, the a sub n's clearly go to 0, but that by itself doesn't tell us anything. Remember, the nth term test, if this limit were not 0, then we would say the series diverges. But we don't have that, so we can't use that. It's not geometric. It's not a p series. It's maybe looks close to a p series, like 1 over n, but it has this natural log of n to the 4th on it. Well, one of the tests that we have is the integral test. And if we think about this function, just replace n with x and think about this function of real numbers, this function is certainly positive for values of x greater than or equal to 2. And it's also continuous. All right, the only problems we would have if x were 0 or getting close to 0, right? We have vertical asymptote for this function there. And then decreasing, it's true because both x and the natural log of x to the 4th are increasing functions, and so 1 over this product is going to get smaller and smaller. So this is true, and so we can integrate this from 2 to infinity. And when we do that, a couple things. I'll first rewrite this as the limit as t goes to infinity, integral 2 to t. And then I'll just notice this natural log of x to the 4th, by the property of logarithms, we can write the natural log of x to the 4th as 4 times the natural log of x. And that makes this problem a lot easier, right? Just making use of the property of logarithms, because we are looking at an exponential expression. What's the exponent on it? When I'm raising a power to another power, we multiply the exponent. So 4 times the natural log of x, which is the exponent on the base e needed to get x. Okay, so now what are we going to do here? Well, I'm going to do a little substitution here. I'm going to let u be the natural log of x. So du is 1 over x dx. And I'm going to change the limits as well. When x is 2, plugging in 2, we get u is the natural log of 2. And when x is t, the upper limit, u is natural log of t. So we do have a 1/4. I'll just pull that out because it's a constant multiple. And I'll take the limit as t goes to infinity to these new limits, and then the dx over x, this part right here, that is equal to the du. And we got the natural log of x down here in the denominator, which is u. So it's the integral of 1 over u. Well, what's the integral of 1 over u? Answer, it's the natural log of u. Now we'll evaluate it at natural log of t, and this is not correct. This should be the natural log of the natural log of t. Sorry about that. Because it's natural log of u, and we're replacing u with natural log of t. So this is the natural log of the natural log of t. And this is natural log of the natural log of 2. However, as t goes to infinity, the natural log of the natural log of t is going to infinity, right? Because natural log of t is an increasing function on its domain, and its limit as t goes to infinity is infinity. Of course, subtracting something going to infinity, this is a finite quantity, the natural log of the natural log of 2, and so we get infinity. What's that mean about this integral? This improper integral diverges, and therefore by the integral test, the series we were looking at, which was the positive term series, right? This one is divergent as well. And that means our series, the original series with the sign changer, right? This series is not absolutely convergent, but it may be conditionally convergent. In other words, it may converge when its absolute value series diverges. And that actually is the case here, because looking at our series now, if I let a sub n be the positive portion again, we do have this sign changer, -1 to the n, making this an alternating series. The limit as n goes to infinity of a sub n is clearly 0. We talked about that already. And a sub n plus 1 is less than or equal to a sub n. If I plug in n plus 1 into my a sub n here, I get this, and that's clearly going to be less than this, and that's true because, again, the functions n and the natural log of n to the fourth are both increasing functions of n. So when I plug in n plus 1, something bigger than n, this denominator here will be bigger than this denominator, making this fraction smaller. But these are the conditions that we need for the alternating series test. And when they're met, we know that the series converges. So this series will converge by the alternating series test. That means this series converges conditionally, right? It's convergent, but the absolute value of the terms, if we add those up, that is divergent. So it converges, it's good, it's just not absolutely convergent, which is really nice. Okay, I hope this makes sense.